Welcome to this guide on how to add meaningful error bars to experimental graphs. Error bars are not just decorative elements or admissions of failure. They are powerful tools that communicate the reliability and reproducibility of your measurements. First, let's understand what error bars actually represent. Many students think error bars are signs of mistakes or bad technique, but that's not correct at all. Error bars quantify the uncertainty in your measurements. They tell your reader how confident you can be in the reported value. They reflect two main sources: real physical variability in the system you're measuring, and limitations of your measurement instruments. When presented properly, error bars make your data points reproducible. Another scientist should be able to repeat your experiment and get values that fall within your error bars. Let me give you an analogy. Imagine you're weighing flour on a kitchen scale. The scale reads to the nearest gram. You weigh the same cup of flour 5 times. You get readings of 247 grams, 248, 247, 249, and 248. The average is 247.8 grams. But notice the spread. The measurements vary by about plus or minus 1 gram. Is this variation your fault? Absolutely not. This spread comes from the fundamental resolution of your scale and possibly tiny air currents or vibrations. Reporting 247.8 plus or minus 1 gram is much more honest and useful than just saying 247.8 grams. The error bar tells the complete story. Now let's talk about how to actually determine error bars. The first and most reliable method is repeated measurements. Take multiple measurements of the same quantity under identical conditions, ideally at least 3 to 5 measurements, but more is better. Calculate the standard deviation of your measurements. This quantifies the spread of your data around the mean value. The standard deviation sigma equals the square root of the sum of squared deviations from the mean, divided by n minus 1. This is the sample standard deviation formula. Use this standard deviation as your error bar. This represents the typical spread of your measurements. Let's work through a concrete example. Suppose you're measuring the spring constant of a spring by hanging different masses and measuring the extension. You hang a 200-gram mass and measure the extension 5 times. You get 3.2 centimeters, 3.4, 3.3, 3.1, and 3.3 centimeters. The mean extension is 3.2 plus 3.4 plus 3.3 plus 3.1 plus 3.3, all divided by 5. That gives us 3.26 centimeters. Now calculate the standard deviation. The deviation squared and summed, divided by 4, then take the square root. We get 0.11 centimeters. So you report the extension as 3.26 plus or minus 0.11 centimeters. This tells the reader exactly how reproducible your measurement is. The second method is using instrument resolution when you can only make one measurement or when repeated measurements give identical readings. Find the smallest division your instrument can read reliably. For a ruler marked in millimeters, that's 1 millimeter. The uncertainty is typically taken as half the smallest division. So for a millimeter ruler, the uncertainty is plus or minus 0.5 millimeters. Here's a ruler with millimeter markings. You're reading a length that falls between markings. The uncertainty is plus or minus 0.5 millimeters because you're estimating between marks. For digital instruments, use the last displayed digit. If a thermometer reads 23.4 degrees Celsius, the uncertainty is about plus or minus 0.1 degrees. You might be wondering, which method is better, repeated measurements or instrument resolution? Repeated measurements are almost always superior because they capture both instrument uncertainty and real system variability. Instrument resolution only captures the uncertainty in reading the instrument, not variations in what you're measuring. The best approach is often to combine both. If your repeated measurements give a standard deviation smaller than the instrument resolution, use the instrument resolution as your error bar. A critical principle: every data point you plot should represent a reproducible measurement, not a single trial. A single trial is essentially anecdotal. It cannot be verified. It has no statistical weight. Each plotted point you put on a graph should be the average of multiple trials. 3 minimum, 5 is better, 10 is excellent. The error bar then shows the spread of those trials, giving the reader confidence that your result is reliable. This is what a good scientific graph looks like. Each data point is the average of multiple measurements, and the error bars show you the reproducibility at each point. Now let's talk about what it means when you have large error bars. Are they bad? Not necessarily. Large error bars often indicate real system variability. The phenomenon you're studying is genuinely variable or unstable. This can actually reveal interesting physics. Perhaps the system is near a phase transition, or there are uncontrolled environmental factors at play. Large error bars also tell you where to focus your efforts to improve the experiment. They highlight which measurements need better control. Consider measuring the coefficient of friction between two surfaces. You pull a block across a table and measure the force required. You might find the friction force varies by 20% between trials. This isn't experimental error in the traditional sense. The surface roughness genuinely varies from spot to spot. Some areas have more contact, some have less. This is real physical variability. Your large error bars communicate this inherent variability. They're telling an important story about the nature of friction on real surfaces. Now let's talk about how to discuss error bars properly in a research paper. This is where many students fall short. In your methods section, explicitly state how error bars were determined. Did you use repeated measurements? How many? Or did you use instrument resolution? Write something like, error bars represent the standard deviation of 5 independent measurements taken under identical conditions. In your results section, discuss what contributes to the uncertainty. Identify the dominant sources of variability. For example, temperature fluctuations in the lab contributed approximately 60% of the observed uncertainty as determined by controlled tests. In your discussion section, interpret what the error bars reveal about the physics of your system. Large error bars near a certain temperature might indicate the system is approaching a phase transition where properties become more sensitive to small perturbations. Decreasing error bars across successive data sets might demonstrate improved experimental control or technique refinement. Always discuss what steps you took to minimize uncertainty. This shows you're a thoughtful experimenter. For example, we enclose the apparatus in a plexiglass box to shield it from air currents, reducing position uncertainty by a factor of 3. Or, all instruments were calibrated against NIST traceable standards before each measurement session to minimize systematic drift. Or, to reduce statistical uncertainty, we increased the number of trials from 3 to 10, which decreased the standard error by a factor of 1.8. When you calculate a quantity from multiple measurements, you need to propagate the errors. This is crucial for derived quantities. If y is a function of several measured variables x1, x2, and so on, then the uncertainty in y involves partial derivatives and the uncertainties of each input variable. Let's see a concrete example. You measure spring constant using Hooke's law, k equals F over x. The spring constant k equals force F divided by extension x. Suppose you measure force as 5.0 plus or minus 0.2 newtons and extension as 10.0 plus or minus 0.5 centimeters. First calculate k. 5 newtons divided by 0.1 meters gives 50 newtons per meter. For division, the fractional uncertainty in k equals the square root of the sum of squared fractional uncertainties in f and x. Plug in the numbers. 0.2 over 5 squared plus 0.5 over 10 squared. That's 0.0016 plus 0.0025. Square root gives 0.064. Multiply by 50 to get the absolute uncertainty. Sigma k equals 3.2 newtons per meter. So you report k equals 50 plus or minus 3 newtons per meter, properly rounded to match the precision of your uncertainty. Let me emphasize, error bars are not weaknesses. They strengthen your scientific credibility when used properly. They demonstrate that you understand the limitations of your measurements and the variability inherent in the system. They make your results reproducible. Another scientist knows what range of values to expect when repeating your experiment. They allow meaningful statistical comparison. You can determine if two measurements are significantly different or consistent within uncertainty. Speaking of statistical comparison, error bars let you assess whether differences are significant or just statistical fluctuations. If the error bars of two data points overlap substantially, the difference between them may not be statistically significant. If error bars don't overlap at all, the difference is likely real and not due to random measurement variation. Here we have two measurements whose error bars don't overlap. This strongly suggests the difference between them is real and statistically significant. Let me give you a real-world research example of how error bars revealed important physics. Researchers were measuring the thermal conductivity of a material near its phase transition temperature. They noticed the error bars grew dramatically as they approached the transition temperature from below. This wasn't poor technique. It revealed critical fluctuations in the material. Near phase transitions, thermal properties become extremely sensitive to tiny variations. The large error bars themselves became a key finding, demonstrating that the material exhibited critical behavior consistent with theoretical predictions. Let me highlight some common mistakes students make with error bars that you should avoid. Mistake number 1, plotting single trial data points without any error bars. This provides no information about reproducibility. Mistake 2, using error bars that are smaller than the symbols used to plot points, if uncertainty is that small, stated in the caption. Mistake 3, calculating derived quantities but ignoring error propagation. All derived quantities must have error bars too. Mistake 4, not explaining what the error bars represent. Always state in the figure caption, error bars represent standard deviation of 5 trials or similar. An advanced topic. Should you use standard deviation or standard error of the mean for your error bars? The standard error equals the standard deviation divided by the square root of the number of measurements. Standard deviation shows the spread of individual measurements. It tells you how much variability exists in the measurement process. Standard error shows how precisely you've determined the mean value. It decreases as you take more measurements. For physical sciences, standard deviation is usually more appropriate because it represents the reproducibility another researcher would experience. Use standard error when you want to emphasize how precisely you've pinned down the true mean value, especially with large sample sizes. Let me give you a practical checklist to use every time you make a graph with error bars. Check 1. Every data point represents at least 3 independent measurements, not a single trial. Check 2. Error bars calculated using proper statistical methods, either standard deviation or instrument resolution. Check 3. Figure caption explicitly states what the error bars represent and how they were calculated. Check 4. Paper text discusses the dominant sources of uncertainty and steps taken to minimize them. Check 5. All derived quantities include properly propagated errors using the appropriate formulas. Let me close with some thoughts on scientific honesty and error bars. Hiding or artificially minimizing error bars is a form of scientific dishonesty. It misrepresents the reliability of your data. Large error bars are not experimental failures. They're information about the nature of what you're studying. Proper error analysis is what separates rigorous science from anecdote. It's what makes your work reproducible and trustworthy. Let me summarize the key principles we've covered. Use repeated measurements whenever possible. This captures both instrumental and system variability. Every plotted point should represent the average of multiple trials, making it reproducible. Calculate error bars using standard deviation from repeated measurements or instrument resolution limits. Always propagate errors properly when calculating quantities derived from multiple measurements. In your paper, discuss what contributes to uncertainty, what you did to minimize it, and what it reveals about your system. Remember that large error bars often reveal important information about system variability or proximity to interesting physical regimes. Properly presented error bars strengthen your scientific credibility by demonstrating that you understand measurement limitations and care about reproducibility.